Pranay, are you there?
Okay.
Yeah,
Yes,
you
I'm
could.
here. Am I audible?
Yes, yes. Please share your screen and then.
Yes. So first, good afternoon to everyone. Okay. First, let me share my screen. Okay. So, is a Chrome window visible right now?
Yes, yeah, it's visible. Yeah, not in a full screen mode, but
Yes. Yes.
it's visible depending on how you want to show it to us. Yeah.
Okay. Okay. Fine.
So you have, I think, Pranay, 15 minutes for your talk and then 5 minutes for questions. So I think I will give you a 2 minute warning in the 13th minute. Okay.
Yes, that works. So, good afternoon, everyone. First, I want to express my heartfelt thanks to the organizers so that I can present my research was ongoing research work. I am Pranoy Ghosh, currently a second year MSc astronomy student at IITI, and what I am working on is the reanalysis of the GMRT All Sky 150 megahertz survey. Mainly, I'm doing it using CASA-based pipeline, which has come recently public, which works for both legacy GMRT and also meant to work for upgraded GMRT. It is being called Capture, and this work is important because it will help me to us to do better constant on low frequency foreground so that we can probe the epoch of reionization at 150 megahertz. So that's how it is relevant for this workshop. Okay, so I am not an expert in the chronology of universe, but as we all know that it all started with the space-time singularity called Big Bang. Then fast forward, we have almost dense intergalactic medium, homogeneous intergalactic medium, which is mostly hydrogen gas. Then fast forward, the first stars and galaxies were forming. So from there, the light sources would also emit the ultraviolet photons that would take us to the epoch of ionization. But from the neutral medium, it will start to get completely ionized. So it is a very important stage in chronology of the universe, but very difficult to probe due to the presence of foregrounds. Now, what is important, relevant for us is that TGSS is at 150 megahertz. So from here we can see that 150 megahertz would correspond to a redshift of 8.5, 8.5 for the 1420 megahertz or the 121 centimeter line, which is relevant for probing the epoch of reionization. So what I am doing is trying to do image the TGSS data, trying to do better calibrations. So let's explain. So what is to be understood? We're trying to see the cosmic dose around epoch or reionization signal, which is actually very weak signal. But in front we have the radiations from extragalactic foregrounds, which is due to the active galactic nucleus, star-forming galaxies, radio halos, and relics, or galactic foregrounds, which is due to free emission, cyclotron emission. These are very strong, and we will have to first model this so that we can subtract out and get the background. That's the intention. Okay, so here we can actually see that how strong the other foregrounds are compared to the Mach 21 centimeter signal, which everyone is after. We can see gradually which signals, which programs are little by little stronger. So galactic synchrotron radiation is the most strong. Okay. So it is actually very important to calibration correctly because even if there are small phase errors remaining, that actually changes the position of the object in sky. So at the end, when we subtract, suddenly we have a position where there is a false negative, another position where there is a false positive. That's why calibration, doing calibration very well is very important. And also TGSS is the only all sky survey from GMRT, which is already in Indian Escape Pathfinder. That's why again this work is relevant for this workshop. Now TGSS is all sky data radio continuum survey data. This is a very important data. The data is very important because the resolution till date it is the highest resolution survey below 200 megahertz, though this is at meter wavelength, its resolution is comparable to the centimeter wavelength surveys. And there has been a public release of the TGSS data, which has been analyzed by a team at Netherlands. The lead is Hub Itima. There is a paper which we can read, and we can see here that how much RMS noise they have managed to brought down. So there are already good quality public images, all sky images, ADR mosaics available in a public website. So why do we need to reanalyze that using new techniques? So one thing to understand is that important surveys are often reanalyzed when new techniques come. One motivation is that people using ADR has reported privately that when they compare it with data from other telescope, there are sometimes a mismatch of flux density. So flux density scale at low frequencies is very important, so that this work becomes immediately required. However, also there is the chances of promoting open science. Earlier, GMRT data were generally processed in AIPS, and AI spam is also based on AIPS spam, which has been used to do the ADR. While capture will be CASA based, and CASA is uh, supposed to do better in terms of when it comes to wideband imaging, which is relevant for legacy GMRT. So capture pipeline mainly targets improvements at wide band frequencies, wideband imaging relevant for upgraded GMRT, but it should also work very well with legacy GMRT data. Also, capture was not tested at the 150 megahertz data, which I am, or band 2, which I am actually doing. Okay, so there is the initial goal of comparative performance, and current limitation of capture is that it doesn't support direction dependent calibration. We can do only self calibration there, while capture includes direction dependent calibrations. So I here want to show you visually or qualitatively how our images look compared to the ADR mosaic. So here I have one pointing, which comes from a observation dated 19 July 2010. So on the left, I have my image, which has undergone 5 self-calibration loops, and this is what I have obtained from the ADR mosaic, which are available in the public website. So no processing involved here. This has been downloaded, and we can see visually it is possible to match sources point 1 to 1. Although we emphasize that our images do not include the direction dependent calibration as ADR. Still, this is qualitatively good, I believe. Similarly, I show for another pointing R69013, which comes from another observation. This observation is 8 July 2010. So this observation files actually contains many more pointing. I am just picking up a sample, one pointing from one date. So same I'll say here. And finally, I show another, the third one, R70D11. This is the pointing, which comes from 29 August 2010. So now when we have seen it qualitatively, now we should try to quantitatively see the compare the RMS noise, etc., dynamic range. So here we are doing this. What we see is that the dynamic range in ADR is supposedly a little better. Here the ratio has been provided. Okay, I'm sorry. Oh, I was unable to see the full screen. Just sorry for interruption. Yeah. Even in one instance, R70D12, we can see we have almost matched the ADR, though we have not included anything other than self-calibration, or otherwise the ADR mosaic will seem to have done slightly better dynamic range. This is primarily because the signal free RMS is lower in case of ADR, where ours is higher. And one thing to notice is that the flux haven't come same, so this requires an investigation. So what we will do right now is that I use a fitting software to extract the point sources from my images and those from the corresponding ADR mosaic, and then I compare the fluxes. Which flux to compare, because there will be two values. So I show for both integrated flux, which is Zansky, which means the beam area has been integrated, and peak flux, which is Zansky for per beam. So for each pointing, when for as many as point sources that could be cataloged and compared by RA I have uh, done the ratio each time and taken the mean, and so here I get the graph. From here, it confirms that in our images the flux is certainly higher than the ADR by a factor less than 2. However, you want to do it whether for integrated flux or for peak flux. So what might be causing it? For this reason, I check the flux from the flux calibrators used in the flux calibrator used in TGSS. There are only 3 flux calibrators used. These are very well known. Okay, and for the raw data I had downloaded, I had used the capture pipeline, and I just stopped before imaging. Just I stopped where I have to do set Zansky and transfer scale. Okay, I used all the 3 standards which should work at this frequency 150 megahertz frequency per Taylor 1999, Skype 2012, and per Butler 2017. We can see that for 3C48 and 3C147 that there is quite a similarity, but for 3C286, as I have extracted this from ADR mosaic, this comes off from what should be expected. Only for 3C286 I see this. Now going further into the investigation, I see the phase calibrators. Okay, so there are 32 phase calibrators, and I could do up to 23 phase calibrators. Here, this is the full table, but slowly I'll just go to one graph that should summarize this. Okay, we can see what it shows that for each phase calibrator, as I have extracted from ADN mosaic, while extracting there is an error because it is this fitting software which is doing it, so it reports an estimate as well as error. Like this, I have done these 3 from my raw data which I have and using capture. I have done this. So each time I have used a standard, there is also a error reported. That's how I get these sets of 3 columns. Okay, so there are 23 phase calibrators in these 2 slides, and I summarize the result in this plot here. What I see is that for most of the phase calibrators, actually, it confirms that our images have a higher flux. Most of the phase calibrator, when taken from our analysis versus ADR, it has shown greater than 1, and only I think 4, sorry, only I think 4 has come less than zero point 0.5, which means the ADR one had a lower flux. So we do see some flux discrepancy, but we need to do further investigation to say what is causing it and whether it is systematic or something else. Okay, so here I can show you the ligands that are the blue one for the Perle Butler scale versus the art extracted from ADR mosaic, while the red ones are for Perle Taylor 99, and the yellow one is for Sky Health 2012. So here I summarize my findings. As I have been explaining, that there is an inconsistency between flux density in the output images as we see from ADR mosaic and our analysis. Okay, we finally thought that it might be because the in theory the difference between our images and the ADR mosaic is that ADR mosaic images includes the direction dependent calibration while we cannot. But let's investigate. We should investigate further to understand this. And in future work, it would be very good if I can include a direction dependent calibration capabilities in capture, because only spam which is AIPS based contains this capability, but no counterpart exists for any casa based pipeline. And finally, I would like to say improved calibration will give high fidelity images, and therefore we shall have a very good, better, accurate knowledge of the foregrounds, so that we can subtract it and get the your background. But one thing, there is also another goal of doing this project. So I was showing that I
So
have
Pranay,
taken.
1 more minute. Okay.
Yes. Had shown that there are 9 pointings. Yeah, you should count. These are the 9 pointings. So these pointings were not taken in random. This actually corresponds to gamma G23 field. So there are several reasons for choosing the gamma G23 field. One is that it has been already well studied in multiple wavelengths using SK, also being studied using SK precursor like the ASCAP. And just 1 minute. Okay, so when we have better images for this field, it is possible to do multi-wavelength study. Just saying this, I would like to stop.
Great.
I'd like
Thank
to
you.
thank you for your patience, and I will also be very happy to get emails and answering all queries. Thank you. So I'll be now open to Q&A sessions.
Okay, great. Thanks. Any questions? Yeah, Desh has a question.
Yes.
Uh, are any one of these sources which show discrepancy, are they polarized, highly polarized?
Sorry, sir.
Have you looked at the polarization properties of the sources,
No, sir, not yet.
particularly in the comparison where they show discrepant trend? It might
No,
be
sir.
worth looking at,
Yes,
what the
yes.
story on the polarization is.
Okay, sir.
Thanks.
Any other questions? So maybe I can ask a quick question. So I'm an outsider to this kind of analysis, Pranay, but just to understand,
Hmm.
I mean, a relevant quantity usually published by such surveys is the luminosity function, right? These source counts, D and DS. Now, the flux discrepancy that you are reporting in this talk, how much of an effect would that have there? Is that a negligible effect in your expectation, or would it be a significant effect?
Actually, I believe these questions are very important, but I do not fully understand. Also new to the to this work. I'm doing this for MSc project, so I haven't actually looked into that function.
Mhm.
So I cannot directly answer, but I definitely after this workshop I'll look into.
Yeah, okay, no problem. Thanks. Any other question? Yeah, Aishrila, you need to be unmuted, right? Yeah. Yeah, go ahead and ask your question. We can't hear you. I don't
Actually, I
think.
cannot hear also.
Yeah. So maybe let's see if she can figure out. Yeah, I don't think you can. We can hear you. Maybe you can push the discussion to Slack or later, Aishrila. So okay, I think we are out of time now. So thanks, Pranay, and thanks, I guess, to both the speakers in this session. And then I'll just give the controls to the organizers.
Thank you.